All right, so day 2 of parametrics. Okay? We're getting closer and closer and closer to all being the man in black, Mr. Johnny Cash. Okay? That will happen on the 20th. We will all become the man in black, so we're black on the 20th because it's Ring of Fire Day on the 20th. Okay? Good times. Okay? All right. So we're going to start today with, I would like you to, on your graphing utility, be it Desmos or a graphing calculator, I would like you to graph this parametric function. Now, in terms of when we go to the graph, just so you know, if we wrote this as three cosine of theta or 3 cosine of t, those mean the same thing, okay? Just that your parameter in this case, the original way we wrote it, your parameter was theta instead of t. And then this one would be y equals 2 sine of t, and t would go from 0 to 2 pi. Same thing, same difference. Okay? Just sometimes it's written. Sometimes the funky cosine ones are written like that. Okay? So you need to be in a parametrics over there. And when we say 3 cosine and 2 sine, 3 cosine, 2 sine. Okay? So 3 cosine t and 2 sine of t. Now, if you're on Desmos, obviously you're typing this 3 cosine of t in the x part of that one, and go there. Okay. Love it, and enter. Yeah. So now you might have to remember, you might have to square up your picture. So on Desmos, that's in the wrench, the little wrench that's over up on the right-hand side. There should be a spot then to zoom square. On the graphing calculators, it's way, whoa, it's way, down here. It's letter B, zoom square. Now, whoa, where did that, hold on, let me get back to window, zoom, standard, there we go, now it's better. Now if I window, zoom, square, gets me the same. But figure out which way things are going here now. Go this way, and bam. There it is. Okay? Love it. Now, what I would like you to do with that same problem is I would like you to attempt, if you will, to eliminate the parameter. And we'll actually do this one together, I think. Sounds like a good plan. What do you think, Emmy? Do this together? Yeah, sounds like a great plan. So the first thing is, come on down now. So we had x equaling 3 cosine of t, and we had y equaling 2 sine of t. Now, from our notes and discussion yesterday, how do we go about eliminating the parameter? We've got to solve for t, right? Okay. Which one do we want to solve for t? Y? Okay, love it. We'll solve y for t. Okay? So if I solve y for t, I'm first going to divide both sides by 2. That's going to give me y over 2 equals sine of t. Still got t inside of a sine, so I'm going to need to inverse sine that to get t. Yes? Okay. Now what do we do? Put that back in for t in the other one, right? Okay. So that's going to be x equals 3 cosine of the inverse sine of y over 2. Right? Now what do I do? Okay, can we simplify it? Looks kind of ugly, doesn't it?
If you could simplify it, you have to.
Yeah, because this is not how you do it. That one's ugly, right? Okay. So we got to do it a different way. And when we do ones that are involving ellipses and circles and all that, the trigonometric function, when we're eliminating the parameter with a trigonometric function, we actually use the hammer. It's been a while since we talked about the hammer. And the hammer, again, was cosine squared of theta plus sine squared of theta is equal to 1. Okay. Well, that can also be written as actually, let me switch this to t's right away. The cosine of t quantity squared plus the sine of t quantity squared is equal to 1. So instead of solving for t, let's solve for the sine of t and the cosine of t. Because now that cosine is x over 3 and sine is y over 2, we can replace those or substitute those in there. And then we get a much more cleaner equation. Now again, had we not skipped over conic sections in first semester, you would know that that equation is the equation of an ellipse with a major axis that is 6 units long and a minor axis that's 4 units long. If I go back up here to my picture, that's an ellipse with a major axis. In this case, it's been stretched out horizontally. So it's stretched out so that the horizontal axis is 6. 1, 2, 3, 4, 5, and 6. So there's my 6 units long. And my vertical axis is 4 units long. 1, 2, 3, and 4. Centered at the origin. So that works out. We just wanted to show you that because that will come back when you get into calculus with parametric equations and eliminating the parameter, changing it from a parametric equation to a rectangular equation. That's another way to say that's what we're doing. Okay? Questions on that? With that being said, we are now back into the brown packet. Okay. At Homer's, again, I apologize. I didn't realize until yesterday afternoon that we never posted the packet online. We have now since posted the packet online, so it's there for you. We are now on page 2, 4, 6, 7, object launched note sheet. Okay? So we are on this sheet now, motion in the plane. It can be shown using some calculus that if an object is thrown or launched vertically, okay, so we're only launching things vertically, okay, so up and it comes straight back down. No wind, we're in a vacuum, all that fun stuff. The only thing that's acting on the object is gravity. Okay? So it goes straight up and it comes straight back down in the same path. Okay? Launches it, goes up. Gravity takes effect, slows it down, ends up stopping it at its highest point, comes back down until it hits the ground. Okay? We're not going with any bounces so far. No bounces today. Okay? Okay? So it's shown that if we do that vertically in the air from initial height of h sub 0, so this is the height. The height of our launch is h sub 0. With an initial velocity so that is a speed, because that's a velocity. And then there's this part. And as you probably learned in science somewhere along the line, that's gravity. That's the gravity part. So we can find the height of our object. Okay? If I said that I'm launching this straight up at 10 feet per second, we can find the height, we can find the maximum height, we can find how long it's in the air, we can find a ton of stuff based off of that. Okay? All off of that one. So that's our height, our vertical motionness of it. Okay? Let's put it to work with the next example here. Next example says from the top of a 30-foot building. So from the top of Wausau West. Okay? You go up there and you take this softball and you throw it vertically upwards with an initial velocity of 50 feet per second. So launch it straight up vertically perfectly, 50 feet per second. What's going to happen to this ball? Let's say we're like literally right at the edge. Okay? So we actually even go like this, so we're over the edge. Okay? Ball's going to do what? Go up, up and up and up and up. Then go down, ends up stopping, right? And then what? It's going to fall back down. And it's actually going to go down farther because we're at the edge, right? Okay? So a picture of that. So here's the edge of the building. Here's the green grass of Wausau West. We know that this is 30 feet right there. And we're standing at the edge. We're standing at the edge. And we take the ball and we throw it up, and it goes up and up and up and up and up. And then it comes back down, 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 and it goes kaplunk. Let's say we're throwing it into mud, so it just goes. It just sticks. So, in function mode, the function that we have there of that, so we could say that S of t, so that's the position function, S of t. We could say that that is negative 16 t squared plus, well, my initial velocity was 50, and my initial height was 30. So we have that function to tell us the height of our softball. Okay? Let's graph that on just a regular old graph on your graphing utility. So I'm going to go here. I'm going to start a brand new, I want a new document. I don't want to save that anymore. I want graphs because I want to be in function mode. Okay? So now, because we're in function mode, or because you're using Desmos, we're going to switch our t's to x's. Okay? That's the difference. We're switching our t's to x's. So negative 16x squared plus 50x plus 30 is our function. Then when I hit enter, you probably, if you're using Desmos, you already see it. We get this, but I can't see it all, can I? Okay. So let's adjust our window. X's, okay, that one doesn't need to be out that far, so let's go -5, because really that's negative time, right? T is time, okay, so that's negative time, so we don't have to go up there. I'm a big fan of going by ones, okay? Y's here now. How high do you think that ball will go? Remember, we start 30 feet up. How high do you think that ball's going to go up? 70 feet? Okay, so we would put 70 then as our maximum. And I'm going to go by tens. Okay, so that's an applicable window. And we get that? Yeah, I would agree. 70 feet works because we can see the top of our function. Yes? Now, I got questions. I got a lot of questions on a lot of things, so a lot of things. Makes my family get a little like, Dad's asking questions. Like when we were at the aquarium in Atlanta on Saturday, I was asking questions, and all of a sudden I looked to go tell my family what I found out, and they were like, "Oh, they didn't want anything to do with me asking my question." Inquisitive mind. How come this graph doesn't look like that graph or that picture? But we didn't factor any of that. We didn't factor any wind, anything else. We did utopian launch conditions. We got Q.
Because X is time.
X is not time. X is time. X is not horizontal distance. Okay? So that is the time that it takes. So we can find certain things out about this one. And this is the nice thing about using a graphing utility. For instance, I can analyze this graph for its maximum point. So the maximum value of the height, or the maximum height of this ball is 69.1 feet. Okay? I can find a zero. This ball is in the air for 3.64 seconds under these conditions. Okay? We can find all that fun stuff. Okay? based off of that function. I should capture that page, and then I should go back here, and then I should go this way. Bring this to there. Okay? Love it. Now, in parametric mode, we can actually, if we switch over to parametric mode, we can actually show this. Let me scroll back up here again. We can actually show that picture, the picture of what we drew to represent the situation. So here's how we do that. Horizontally, this ball is not traveling anywhere horizontally, right? It's going straight up and it's coming straight back down in the same spot. So we can put here any number. I don't care what number you pick, you can put any number there. Okay? In your Y one, you're going to put your function, except now it's going to stay with the t values. Okay. So when I go to my graphing utility, now I'm going to switch this. I'm going to add a page, add a graph, switch this to parametrics. I can pick any number that I want. I'm going to pick 6. I can pick, and then I put in here negative 16t squared plus 50t plus 30. And my t-step, my t-range, if you will, can be any number as long as it's bigger than 3.64. If it's smaller than 3.64, our ball is never going to hit the ground. But if it's bigger, it's just going to, on the graph, it's going to look like it's going through the ground. Okay? So I'm going to switch this to 4. There's my function. Now again, I should adjust my window so that I can see everything. X's were good there. Here, there. 1. Whoa, 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 whoa. Come back to me. Don't be doing this to me now. Don't you do it. It did it. Trying to do this fast. Y's, -5, 70 we said. Come on. And there's the path of our ball. And there's the situation. We could even draw in, if we wanted to, we could draw in our building here. Oops, the building would actually be down here. 5, 10, 15, 20, 25, 30. Building would be there. Okay. Love it. But, like we were saying before, we don't always launch stuff at an angle or launch stuff straight up in the air. Most of the time, we launch stuff at an angle. Okay, right? So that the ball not only has a vertical component, it also has a horizontal component. Oh, hit the chair. Okay? What? Were you worried for the TV? I wasn't. Okay? Right? So it's got a horizontal and a vertical component. Now, when you are throwing a ball, and I'm sure that all of you have thrown something in your time, okay? In your years around walking or roaming this planet, I think you've thrown something, sticks, whatever, okay? So whatever object you have, balls, you kicking things. Some of you guys are soccer players, okay? You kick stuff, same concept, okay? Right? As soon as that object leaves your hand, you have no control over it anymore. Okay? It's all in the other forces that are going on with it. Okay? So as soon as an object leaves your hand, it's on a vector. Okay? It's on a vector course. Okay? Now, once it leaves your hand, then gravity takes effect again on it. Okay? So if we're throwing it without a wind here, like we are in here, when it leaves my hand, now gravity, it's still going to have that upward component to it because I'm throwing it at an angle. Gravity's going to take effect of it. It's going to stop, or it's going to stop rising, and then it's going to start falling. It's still going to have a horizontal component because it's still going to be going out, okay? And it'll fall in a parabola. So what we need is an initial velocity vector. Okay? So what we need is this blue vector here. Okay? Because when it leaves the hand or leaves the launching device, so we need that vector. And that vector is going to be v sub 0 times the cosine of my launch angle and v sub 0 times the sine of my launch angle. So our parametric equation that we will then be using looks like this. Okay? This is the bottom of that page now. It's on the bottom of that page. Okay? So our parametric equation for an object that gets launched from an initial height of h sub 0 with an initial velocity of v sub 0 at an angle theta sub 0, lots of sub zeros there, can be represented by that. And what we can do with that now is we can find the maximum height. We can fit in. We can find the distance. How far away the ball's going to land or the object's going to land. We can find time in the air. We can do tons of stuff with it. Now, a few years ago, we saw, do you have questions on?
What was the last thing you had written on the last slide?
On the last slide? It was just the initial velocity vector.
Oh, okay.
Yep. Which is where we got that information from. Okay? Now, a few years ago, if you're a Packer fan, okay, we saw multiple examples of this happening during a season. Okay? One of the best ones was, get it from over here. Miracle in Motown. Okay? So, and I actually, after this came out, ESPN has sports science and all that stuff on it, and they figured out how high the ball went, and it almost touched the ceiling of Ford Field, and they showed how it was perfectly propped, like how it perfectly landed. They could show exactly where it was going to land, and all this fun stuff. It's pretty cool. Okay, all right. So we got that going on. All right, now I got to come back to this. Okay, so let's do a problem. Okay, now this problem it should be on your. Oh shit, that's mine. That's yours. Okay, so Big Al hits a ball at an angle of 28 degrees. Does anybody in the room know who Big Al is? There we go. We got a couple of people who don't know. Okay, so for those of you that don't know, this is Big Al. And he hit dingers. They've been, for the Little League World Series last couple of years, they would have the kids do their own introductions, and then they got creative with it. They let the kids choose, and that was Big Al. Okay, all right. So there's Big Al. Big Al's up to the plate. Okay, we want to know if Big Al hit a dinger. Okay, so he hits a ball at an angle of 28 degrees with an initial velocity of 75 feet per second at a height of 3.5 feet. Will he hit a home run if the ball follows the left field line where the Little League fence is 190 feet away and the fence is 4 feet high? Okay, all right. So let's create this scenario for us right now. Okay. Oops, I went a little too far. 28 degrees. 28 degrees in there. Okay. So let's talk about the ball. So the ball, I'm going to use the parametric equation that we just had. Okay, because we're launching it at an angle with an initial velocity and an initial height. Okay, so the x part of the parametric equation is going to be 75, because that's his initial velocity, times the cosine of 28 degrees times t. Yes? Okay. The y component, the vertical component of the ball, is going to be negative 16t squared plus 75 sine of 28 degrees times t plus the initial height, 3.5 feet. Yes, ma'am.
For the y equation, is it going to be negative 16?
T squared all the time.
For anything?
Gravity constant. Yep.
Okay.
Yep. Yep.
And
That's,
then
you just substitute in the different velocities, different ends, yep, and different initial heights. Yep. Okay. So we got that. Yes. Love it. Let's make that. Well, let's take some time here now and let's put that on your graphing utility. Okay. So if you've got Desmos, this function. If you've got a graphing calculator, graphing calculator, this function. So when we hit enter, that's what we see. We got to adjust our window. X's. So x is the horizontal distance, right? So we don't really care about negative because Big L's not going to hit a dinger backwards. Okay? So I'm going to go -5 there because I like to see my axes. How far out do I need to go? We'll get there in a minute. Yep. Because
We don't see it.
I know. Because I know the two spots where you're missing. How far out do we need to go? Well, where's the wall? 190 feet, right? So we should go out probably past that a little bit. So let's go to 200. Okay. Height. Don't really need to get negative because he's not going to hit a dinger underground. How high do you think this ball gets? $30 maybe? Baseball players in the house. 30 feet. Right? I mean, maybe. I mean, that's 3 stories, if you think about it. I would go 30. We'll go by 5 there this time. Yep, okay, there it is. Okay? So that's what your graph should look like. Now, your first question, Emmy, was, what do we put our t values to be, right? If you don't see this curve hit the ground, you didn't go far enough. Okay? So if you only see this, that ball never hit the ground. So you gotta make your T go longer. Okay? Until that T crosses the x-axis. Then you know it hits the ground. Yes, ma'am? Let me guess. Your graph goes backwards. Yeah. So on Desmos, you're in radians automatically. So you need to go over to the wrench in Desmos and switch it to degrees.
Oh, so that's how I get it to stop
Yep.
working.
Okay. On the graphing calculators, if you put that degree symbol there like I did, then it overrides your radians. Pi, and then it's a choice down in the pi key. Okay? All right? So now we've got that. Yes? Love it. Excited for it. Okay? So now let's go back, and now let's build the wall, the outfield fence. How far away is that outfield fence? 190 feet, so that's my x. It's 190 feet away from me horizontally. So my x value is set at 190. There's my wall. Now we just have to build it up, buttercup. So my y component is going to be t. How high do I want my wall to be? 4 feet high. So I'm going to run this t to 4 because that makes it going to go up to 4 feet high. If I wanted it to be 0.5t, if I put 0.5 as my y value, I'd have to run my t up to 8 to get to a 4-foot high wall. With me? If I make it 8t, I'd have to run it to 0.5. Okay? So now we can input that one onto the same graph. So I want it to be 190 feet away. I want it to be t, and I want my t to go to 4. And there is my wall. did Big Al hit a dinger? Big Al did not hit a dinger in this case, because the ball, the blue line here, is the path of the ball, and the red line here is the wall. So he hit a lazy fly ball to the left fielder. So he did not hit a dinger. Now, what we can do with that, with my blue equation, or your first equation, or your first parametric, is we can adjust it. We can say, we can ask, well, how much harder does Big Al need to make contact with the ball? How much harder does he need to swing under those conditions to get a home run? Or what angle could have he hit the ball to hit a home run? So in the next couple of minutes, play around with this velocity, the 75 there. Play around with this 75 or this 28 degrees and see if you can come up with a scenario where Big Al hits a dinger.